Hi, my name is Samantha Cohen. I work here at Accurx. I'm a staff engineer. I don't have a blue lanyard because I lost it, but I'm getting a new one. And I'm here to talk about this thing that I've been obsessed with for about a year, which I've been calling lexical complexity. And I'll explain it here.
Blue. If it's red, then it's...
I made it blue. I made it blue again. Okay. So where are the notes? I've clearly done this before. There we go. So, oh yeah, there's animations. So in human language, in English and other languages, I'm sure, you can have different levels of complexity.
Can we be louder, or would you like the mic? Does not amplify. That mic only records.
I don't think I can talk much louder. Hello, is that better?
Yeah.
There we go. Where's the clicky? So here's an extract from James Joyce. He wrote some book, Ulysses or whatever. I don't know what the hell this means. Clicky? Oh, I didn't bind. Oh, Jesus, click. Hey, there we go. There we go. And then here's Dr. Seuss, famously easier to understand. Now, in English language, in writing and literature, there's like good reasons for picking one over the other or whatever. Did you want a photo? Too late. In programming, that's not necessarily true or ever true. So these two things do the same, but one of them is sort of clearly more complicated than the other, clearly harder to understand. Maybe it's not much harder, but it is harder. If I'm talking too fast, someone let me know, because it's a habit I've got. But I've got a lot of slides to go through, so maybe just try and keep up. Cool. Hypothesis. Complex things are harder to understand. I think that's tautological, actually. Modifying code correctly requires understanding it. Maybe not with AI, but I still think so. Complex code takes longer to work with. Complex code is more bug-prone when modified. And complex code is more expensive as a result. So what's next? That animation's wrong. So my goal was to find a way to analyze code complexity. Well, the goal came after the wave of inspiration, but whatever. Find a way to analyze complexity. It should be static analysis, and it should reflect the human experience. It should be a representation of the human experience of trying to understand something. Oh, and it should be language agnostic, because that's just better, frankly. So code is not art, it is functional, and the complexity itself has no benefit beyond, like, you can imagine for any set of features, there's a certain minimum complexity, right, that would accomplish the goals of those features. You would not want to go above that for any real reason. Cool. What kind of complexity? So I did a bunch of research, again, after the wave of inspiration, and I found a few different types of complexity. Kolmogorov complexity is sort of from the early days of computer science, and this is all about what is the shortest program that can achieve some goal. And this is, I'll get onto it later. Cyclomatic complexity, I'm sure a lot of us know this. This is sort of the executional complexity of a system, like the complexity of the pathways it can travel as it's executed. And then this was my own addition, coupling cohesion connaissance. These are like fundamental properties of software, and I don't fully agree necessarily with including them here, but I haven't edited the talk enough. And then there's a bunch of others that I only encountered later that I didn't have time to research. So I've already explained this one. The problem, but just a reminder, is the length of the shortest program that can produce a given output. It's a property of the output of the program rather than a property of the code. So it's nothing to do with comprehension. And you also can't compute it. It's basically the halting problem, if I understood it correctly, or it's the same kind of problem. Cyclomatic is the number of independent paths, is a measure of the complexity of execution. It's useful, but it's limited to branching conditionals. Interestingly enough, I've been doing a bunch of analysis, and my lexical complexity metric has a really strong correlation with this. So maybe I undersold it here. But, and finally, coupling cohesion connaissance, very powerful, but it's qualitative. And if you know anything about connaissances, the dynamic ones are inherently uncomputable. It's runtime issues, basically.
Can I ask a question?
Yes, no, yes. Connaissance, there's a really good talk by Marco Consolato about it. It's basically coupling, but like expanded upon and sort of given different categories. So you have static connascence. So connascence is born together, co-nascent. So if two things are created together, they need to change together. So if you have like a string over here that is meaningful and you use the same string over there and it's meaningful, you have to change them together or you'll break the system, which is why you should probably use a variable instead. And it goes further than that. Race conditions are explained by connascence, for example. It's an interesting subject. None of them really tell us if which one of these is more complicated, right? Fundamental gap. I need some water. 1 second. So, I forgot about this one. Cool. Entropy. Entropy is often misunderstood. I have a physics degree, so actually, funny enough, it was during a talk about connascence by Marco Consolaro that I came up with this whole idea, because he mentioned code entropy at the end, and I'm like, oh, that's an interesting thought. I think when software engineers think of entropy, they think of like the progression of a code base to nonsense, basically. But I studied physics, so what I think of is statistical mechanics, and I'll get onto that in a minute. Physical measure from thermodynamics, the amount of energy available in a system. It has found mathematically related definitions in several fields, including statistical mechanics and information theory. So the information theory one is Shannon entropy. That is not what I'm talking about, so we don't need to talk about it. It could come in later, though, which is kind of interesting. But yeah, so Shannon entropy is like a measure of the amount of surprisal of a piece of information. Like, how surprising is this information? If it's one of two and it was one of them, that's not that surprising. But if it's one of 1,000 and it's one of them, that's very surprising. Shannon entropy. StatMech, this is all about how many configurations you can make of how many microstates you can create of a system. So how many different ways can you rearrange the atoms in a glass of water and it still be more or less that same glass of water, right? The answer is a lot. So there's maths in this, I'm sorry. Also, yeah, I didn't even mention, this isn't particularly a .NET talk. This is just a talk. It's more of a maths talk, actually. I hope you're ready. So entropy is defined in S as K, L, and omega. K is a constant. We don't need to worry. Ln is the natural logarithm. We all know about log base 2. This is just log base E. It's more or less the same thing. And then omega is the number of microstates in a system, which is what I'll talk about now. So imagine you have two apples, a red and a green one. Okay, you can arrange it like that. Well, actually, okay, the red and the green is just for demonstrating they're actually the same color. You can't differentiate between them. So if you swap them around, it's still the same system. Does that make sense? Cool. 2 macrostates. Easy. So omega is 2. There we go. And then we have 2 macrostates, so omega is 2. And then the natural logarithm of 2 is 0.69. Cool. What if we had 5 apples? So I really oversold these apples. There's a lot of ways to rearrange these. Did I click? There we go. Factorial, in fact. Do we know factorials? It's yeah, great. Click. There we go. There we go. There we go. I'm glad I got a laugh because we've been so awkward otherwise. Cool. So the entropy of that is the omega is 120, ln of 120 is 4.7. Cool. That's how statistical StatMech entropy works. So the entropy increases as the number of particles in the system increase. So if we applied some structure, what would happen? So let's say instead of 5 apples, we have 2 boxes, and each of those boxes had 3 and 2 apples. You checking my maths over there? I hope it was right, because there's a lot of apples. So what if we do this? Now there's much fewer rearrangements that keep the same system. So you can rearrange the boxes. We have 2 there. Click. Click. Oh, God. you can rearrange the apples in the first box 6 different ways. You can rearrange the apples in the second box 2 different ways. So then ln2 is 0.6, ln2 is 0.69, and then ln6 is 1.79. Add them all together, and then you end up with 3.178. Cool. The fucking maths. So, to compare, we had the unstructured one with an entropy of 4.79. We have the structured one with an entropy of 3.178. All we've done is create some boxes and put the apples in the boxes, and we've reduced the entropy of the system. I just said that. Okay. So, back on code, back on the point of the talk. You have one large file. It is 1,000 lines long. You have a different file with 4 different functions. Each of them is 250 lines. The same number of lines, but one of them has more structure. What do we end up with? If we treat each function like a box, just like that. There we go. File 1 is 5,900, and file 2 is 4,500. So we've reduced the entropy by applying structure. Isn't that cool? So, what's your first piece of feedback when you see a 1,000 line piece of code?
Close it.
What?
Just close the tab.
Close the tab. Can you try splitting it? Yeah, easy. So, the S number, this S number seems to reduce the refactor our code. So what is this number? So the idea comes from entropy, but I've not really been calling it entropy because it feels different. I've been calling it complexity. Boom. The inspiration for this is like, as you're looking at a big piece of unstructured code, you need to understand how everything inside of it relates to each other. Whereas if you create the structure, you have less to comprehend when you're just working through it. So, lines of code is a bit crude. How can we do a bit better? We can use an abstract syntax tree. Is everyone familiar with this? Everyone know what this is? When you write code, the structure of it is defined or sort of passed into an abstract syntax tree. It is deterministic, and it is like a direct representation of your code. I'm thirsty. So I apologize. This is TypeScript, but they had an AST viewer that I could access online. So there we go. The whole source file is one of the boxes. Then the syntax list is one of the boxes. The expression statement, call expression, etc., etc. And you can see the lines matching up. There's the dot token, the identifier, blah 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 blah. So I thought I would use this. How many different boxes do we have? What are the numbers? There we go. This is a slightly boring slide. There we go. We got a 5.6 in the complexity, whatever. If we take the more complex version, so just a reminder, oh my God. I don't think I needed to animate this. I got a bit animate happy. This is just console log hi. And then this one is, there we go. Where is it? There we go. You add a variable. This is an interesting property of the analyzer, which is that it doesn't really like unnecessary variables, which might seem right or might seem wrong to you, depending on your perspective. But the maths works out, so I guess we'll go with it. There we go. That's what you end up with. And 8.8. So by adding the variable, you end up with like 3 more complexity. There we go. Cool. So now we have a system that can analyze the complexity that everything else misses. And you know what else is a tree? File systems. So you can apply exactly the same properties to the file system. For example, there we go, there we go, there we go. You get the picture. And by combining these, you end up with a sort of fractal's a bit rich. You end up with a system that can analyze all the way from the file structure down to the individual line of code, down to the individual expression on the individual line of code. And you can compute the complexity for the entire project. And it's the same number. You could have a single file that is more complex than an entire project. You could have a single line of code that's more complex than an entire project. And that's pretty cool, I thought. It's a universal measure of software complexity. I did a good job with the animations again. There we go. Any project, any structure, any line of code, any language. There we go. I call it lexical complexity. as far as I can tell, this does not exist yet. So I can call it whatever I want. Now, it might seem arbitrary, but it's a computational property of software systems. It exists in every software system, and it can be tested empirically. I came up with a bunch of hypotheses. Not all of these are easy to test, but fine. Projects that have been abandoned due to technical debt will have a very high complexity. Code bases should have their complexity decrease following refactors. Complexity should increase as more functionality is added. I guess I should say refactors by experts. Complexity should increase as more functionality is added. Complexity per lock should be low and written by more experienced engineers, etc. Complexity density, we call it now. Code bases with high complexity should have a greater tendency to increase that complexity with new additions. There's another screen there, I just realized. It's good. High complexity should be more difficult to contribute to, with those contributions taking longer. More bugs should match up with cyclomatic complexity. I may have proven this now, actually. So I prototyped an analyzer in TypeScript, analyzed 100 repos, and I found some results that were very interesting to me. So to me, it seemed like we could see also, okay, complexity and lines of code are positively correlated. There's no surprise there. The more lines of code, the more complex it is. That's trivial, almost. Fine. This one was where I started thinking there might be something more here. So this is the complexity per line of code versus the number of lines of code. So the bigger a project is, the actual density of the complexity seems to start reducing. And that's encouraging. That means maybe projects that survive longer have a bias to be less complex, for example. And then I did also do file density, but I didn't include that graph. And then I rewrote it in Rust. Sorry, it wasn't .NET. And click. There we go. I got 700 times speed increase. I think, what was I analyzing at the time? I was analyzing Microsoft TypeScript. It used to be 8 hours to do the analysis in the TypeScript project. It was 40 seconds in Rust. And now I can do that in probably a second because I've done a lot of optimization. Thank you, Cyril. Cool. I optimized and expanded, analysis in seconds, and now I have a full history analysis. So you can pick a repo, I'll go through the full history of it, I'll analyze everything. And then I ran that analysis on like 700 repos. So here's an example of some of the output. And you can see there's all kinds of, what am I even showing you here? You can obviously see the complexity going up with time, and the lines of code go up with time, and the years go up with time, and the file count goes up with time. But you can see that the complexity densities tend to like reach certain points, and you can see different refactors and different large changes and contributions that affect the complexity per line of code. So you can see that it's measuring something. It's not 100% clear what it is, and it's still not proven that it is meaningful or valuable or important, but I'm working on it. There you go. You can see the complexity going up. Yeah, so you can see what, there was a big code deletion maybe, or there was a refactor to make things simpler, or there was a bunch of maybe generated code added where it starts to spike up again. There's all kinds of things that could be happening. And usually I will go into these projects and these interesting commits and I will like figure out what happened. And it's an interesting history exercise. Okay. I don't have anything to say about that. Cool. So this was the first result that really excited me and showed me something. So here's C#. So what this is all of the C# files that I analyzed, I plotted lines of code against complexity. Because we know it goes up, but what we don't know is what that looks like in different languages. And what I found is that different languages have actually quite different characteristic curves. JavaScript. C# and Java are very similar, but C# has a slightly different shape. What does it mean? I'm not 100% sure, but it's cool. TypeScript to me looks like a cross between JavaScript and C#, which makes sense because of who wrote it. And then what do we have over there? We have HTML, which looks more like JavaScript than anything, and Rust. because I wrote the system in Rust. So you can see like there are different characteristics for different languages, and that's got to mean something, right? It's at least interesting. And this is all of the different languages plotted on top of each other. Slightly roughly, I did it in GIMP. But yeah, I thought it was pretty cool. How much time have I had so far? I think this is a faster talk than I thought it was.
23 minutes.
What? Oh, wow. I'm almost done. I thought this would be an hour. Okay.
I do recall you said, I've got so many slides that will probably take an hour.
Well, I thought it was going to take an hour. I got to talk slower. I got to talk a lot slower.
We're good.
Okay. Well, okay, it's fine. So what next? Maybe I can ad-lib a bit about what I've been doing since then, because I didn't get to update this talk with the more recent stuff I've been doing. So I have built a VS Code plugin, like a prototype VS Code plugin that does kind of work, or it does work. It's not exactly production ready, but it's interesting to be able to like reload the file, like change the file and have it immediately update, and that's pretty cool. And like having direct feedback on the lexical complexity could be interesting. And if you include stuff like cyclomatic complexity in that analysis, then you end up with something that's richer. Because the cyclomatic, it tends to be less critical of the stuff. My algorithm tends to be less critical of the stuff that cyclomatic complexity cares a lot about. For example, the branching ifs, my algorithm doesn't care too much. But if you include the cyclomatic stuff, then you can sort of cover both bases. So this third point, more interesting analyses of the data. I bought a Claude Code license on Saturday, and I've been going a bit crazy with it, to be honest. And I've been using, because I've got probably 500 gigabytes of data on different projects on my computer at home. And I've been using Claude to write like all of the stuff I couldn't quite figure out how to do the analyses for, like multivariate analysis and linear regressions of things and all kinds of stuff. And what we found are two really strong signals that I need to investigate really deeply because AI loves to tell me how smart I am. But the first one is complexity seems to correlate very strongly, like 70% or something, with the volatility of that complexity. So as a system gets more complex, it tends to attract and undergo bigger structural changes, which is very interesting. Maybe it's obvious. I'm not sure. I haven't figured it out yet. And the second one is it's got like a 95% correlation with cyclomatic complexity, which is kind of one of the gold standards I was looking for, is like an established complexity metric that proves this thing is measuring aligned with that. God, I have gone fast. And then try to correlate complexity changes to type of change using commit messages. Yeah, we're doing that, sort of the bug. So that might be the gold standard, is like how many bug fixes do we have on a given file, and does that relate to the complexity? And I imagine it will. Like the real magic is mapping it to the complexity, but controlling for lines of code. So it's not just like how long the file is, it's how much stuff is in there and how complex it all is and how difficult it is to work with. So, God, that was only 25 minutes. There we go. Thank you.